I got two more little things that I want to talk about before I call this section good. And I'm actually going to go out of order from my notes because I think it might make the most sense to learn this next one next. So in the previous video, we learned about what's called the defining characteristic of a function, namely that you can't have two different outputs for a given input, and a way that you can verify that if you have the graph, this thing called the vertical line test. In this video, I want to talk more about this picture. As we talked about in the previous video, it's totally fine to have two different inputs that lead to the same output. That's totally fine. Happens all the time when we're talking about functions. But it doesn't always happen. Maybe we can consider a really simple function like, I don't know, f of x equals x plus 2. All this machine does is you put a number in and it spits out a number that's 2 larger than that number that you put in. Maybe if you're really picking these up, you can see how if I asked you a question like what you see down here, where I give you the output and I ask you for the input, so I give you an output of like, I don't know, 100 and I ask you for the input, you're only going to have one answer. Because of the kind of simple nature of this function, all it does is add 2 to the input. The input is always just going to be the number that's 2 less than the output. So if I asked you to solve f of x equals 100, you would just say that x is equal to 98. Easy enough. You wouldn't have a second answer here. You'd only have one answer. Over here, when I ask you to solve f of x equals 2, you have two answers, 1 and 5. Over here, when I ask you to solve f of x equals 100, you only have one answer, 98. Sometimes you have more than one answer for this second of the two most common types of questions that I went over in a previous video. Sometimes you only have one answer. If you always only have one answer, like we do in purple here, you have a special type of function. They're both functions. These are just special types of them. They deserve a special name. That name is what I want to present to you in this video. That name is it's a one-to-one function. I could give you a definition of a one-to-one function, but you end up with a lot of negations, kind of double negatives in there, and it gets really confusing. So I think it's easier to understand what is not a one-to-one function. A function is not one-to-one if there are two different inputs that correspond with the same output. I think most of the functions we've seen so far fit that bill, right? This first function, f of x equals x squared minus 2x minus 8. When I asked you to solve f of x equals 0, I'm asking you what inputs correspond with an output of 0. And because you provide for me two different answers, -2 and +4, we know that this function f is not one-to-one. To be clear, I'm not saying that there are always two different inputs for a given output. I'm just saying there's at least one output that has two different inputs that correspond with it. So for example, down here, there's only one input, the number 1, that corresponds with an output of -9. But that doesn't make the function one-to-one. In order for a function to be one-to-one, it has to be like this, loosely speaking, for every single output. And this function f of x is not like that. There is at least one output, 0 for example, that has two different inputs that correspond with it. Therefore, this function is not one-to-one. Same thing down here. If I take a given output like, I don't know, -5 maybe, I see that there are two different inputs, -1 and +3, that lead to an output of -5. Therefore, this function is not one-to-one. If I give you a function like f of x equals x squared minus 2x minus 8, in its equation, in its standard form, it's pretty hard and unfair at this point in the class to ask you whether this function is one-to-one. I mean, you could play with it a little bit and put in some inputs and keep track of the outputs and see if you can find two different inputs that lead to the same output and therefore make your conclusion. But that's a little bit beyond what we should be doing in our class. But what I want you to be able to do in our class is if I give you the graph of a function, so I don't give you this equation anymore, I just give you the graph pictured in red. I want to be able to ask you the question, does this graph represent a one-to-one function? First off, because it passes the vertical line test, it definitely represents a function, right? Make sure you can see that this graph in red passes the vertical line test, that any vertical line would only intersect the graph in one spot, and therefore this graph represents a function. But is that function one-to-one? Well, to answer that, we have to think about what it means to be one-to-one. Note that the points -2, 0 and 4, 0 both fall on this graph. What that means is when I put -2 into this machine, 0 comes out, and when I put 4 into this machine, 0 comes out, which is totally fine for a function. That's okay. It just means that function is not one-to-one. I have two different inputs leading to the same output. I'm not violating the defining characteristic of a function. I'm just deciding that this function is not one-to-one. And you don't have to focus on those specific points. When I put 0 into this machine, -8 comes out. When I put 2 into this machine, -8 comes out. Therefore, this function is not one-to-one. If there are ever two different inputs that have the exact same output, the function is not one-to-one. So it's kind of like this defining characteristic that we saw up here, except it's sort of flipped. Instead of two different outputs with the same input, it's two different inputs with the same output. Just like I had this fancy test up here, this thing that I called the vertical line test to decide whether a graph represented a function. I have a fancy test down here called the horizontal line test, which I can use to figure out whether the graph of a function is one-to-one or not. The horizontal line test is almost identical to the vertical line test. What it says is if you can draw a horizontal line, not a vertical line, that intersects the graph of a function in more than one spot, then that function is not one-to-one. It doesn't tell you whether the graph is a function, it tells you whether the graph is one-to-one. So for example, if I gave you this function in red, I didn't give you the equation at all, but I gave you the graph of the function here and asked you the question, could you draw a horizontal line that would intersect the graph in more than one spot? You'd be like, yeah, that's super easy. Here's one, for example. This line intersects the graph in two spots. It intersects it right here and it intersects it right here. Therefore, this graph is not one-to-one. Much like the vertical line test, I'm not claiming that all horizontal lines intersect the graph in more than one spot. I could very carefully draw a horizontal line down here that only intersects the graph in one spot, or even a horizontal line down here that doesn't intersect the graph at all. I'm not claiming that all horizontal lines intersect the graph in more than one spot. I'm just saying that it's possible to draw a horizontal line that intersects the graph in more than one spot. Therefore, the graph is not one-to-one. And so if you can't draw such a line, well, then the graph is one-to-one. What would an example of such a graph look like? Well, here's a kind of complicated one. It's a function that I think I looked at briefly in the very first video in this section. G of x equals the square root of x minus 5 divided by x minus 10. It's beyond the scope of this class to figure out that the graph of the function given by this equation is what's shown in blue. But I can tell you that it is. Note that it is not possible to draw a horizontal line that intersects this graph in more than one spot. No matter which one you choose, it's only going to intersect the graph in one spot, even though it has this weird asymptotic behavior going on here, stuff that we'll learn later on in this class. The point is just the function graphed in blue is one-to-one, but the function graphed in red is not one-to-one. That's all I have on one-to-one functions.